So, basically now we move to the second type of block transceivers where we use cyclic prefix, but this one actually requires some amount of motivation because 0 padded works. What is wrong? Why do not you just go along with that? Okay. So, there is a complexity in terms of the Moore-Penrose pseudo inverse, that is a non-trivial operation, and this matrix could be large because you could have 1000 channels. So, which means that okay, it is not going to be as straightforward to do the inversion, but let us see if there is a advantage and a preferred way that we can do. So, here is a question that or a pictorial representation. Now, if the 0 padding had not been done, if 0 padding not done, okay, what would have happened? You would have seen leakage of one block to another block. So, let us take the case where nu plus 1 equal to 3, that was the channel that we considered. Now, if I had a block of m signal samples, okay, dot dot dot. So, this is 0, 1, 2, m minus 1. I insert 2 0 valued samples, then the next block begins. Okay, then the next block begins. So, this is the 0 padding process. Now, if this 0 padding had not been there, maybe one observation. That means the previous block also had 0 padding, right? Every block has 0 padding. So, I can associate my block now as the block followed by 0 padding, or equally I can do it as the block with zeros in the beginning followed by the 0. Now, I would like to take the second version where I have zeros in the beginning. Okay. Now, if these zeros were not present, what would have happened? I would have had this block, right, I would have had this block of data, and there would have been the previous block of data which came all the way up to the end because the 0 padding was not there, okay. And there is a 2 tap ISI channel, which means that this signal would have suffered from ISI, this signal also would have suffered from ISI. From this point on, I am okay. Right. So, basically because of the 2 tap, so effectively the block interference was felt by the first 2 symbols. Okay. So, the notion that says that okay, you have to somehow, if you want to protect these the first 2 symbols from ISI, the best thing is to insert zeros. However, the option number 2 that we are going to be considering says that take this vector, this block of data, let the last 2 samples be this. You still have to protect your, the protection will come by inserting the last 2 symbols here. Okay, so, these are my new symbols, those are going to be inserted here. Okay. So, which means that I still have a block which is equal to n equal to m plus nu. So, this is my block. I have taken the last new samples where nu is the number of taps of the symbol and put it in the front. So, do I have IBI? Do I have IBI? Which are the 2 samples that will have IBI? This is a channel filtering is a continuous process, right? It is a continuous. So, this will have IBI, this will have IBI, but notice my block of data is okay, right? My block of data is okay. But what about this one, the first sample here? It has ISI, but it has it from itself, from its own sample. So, in one way I have mitigated the problem by saying okay, if I throw away the first new samples, they are the ones that have IBI from the previous block. But what I am left with is a block of m samples where there is block from interference from within myself, but maybe that is a better way. So, here is the summary of the cyclic prefix. Do you understand cyclic prefix? Whatever is the value of nu, I take the last new samples of the block and then put it up front. Okay, last new feed it. So basically you still have a longer block, the redundancy is coming in not in the form of zeros, but is in the coming of non-zero samples which are from your own data block. So the so this is CP insertion. So what we are seeing here is CP insertion. It basically means the new samples from the end are introduced at the front. Okay, and this also means that there is no interblock interference once I have removed the first new samples. So no IBI after the first new samples are removed. Okay, after the first new samples are removed, that is a correct statement. Also it has ISI, but that is what we will say here, intra-block interference is present, intra-block interference, but all the samples have intra-block and all the intra-block interference is from within itself, it does not come from outside. Okay, so this is a useful observation for us to keep in mind and also build upon. Now I need you to quickly work with me on the following example. Okay, I am going to ask you to do a linear convolution but write it in matrix form. So this is an example and it's kind of it requires a little bit of writing down, but please do that it's a helpful example. So basically I want to do a linear convolution of a sequence of 8 samples x0, x1 through x7. Okay, there are 8 samples, so m equal to 8. I want to do linear convolution, asterisk is linear convolution, want to convolve it with a channel response C0, C1, C2, C3, C4. Okay. So this is a case where nu equal to 4. Okay. So basically we would have to write down a matrix and show how the convolution occurs, and I am sure this is something that you can write down fairly easily. Let me just sort of start you off on this. The first entry is H0 and the vector multiply and the sample. So here is the vector x0, x1, x2, x7. That is my vector. I am going to draw it a little bit larger than necessary. In a minute you will see why. So my matrix. Okay. So this is the not equal to, yeah, this is what has to multiply. The second entry in your convolution matrix will be H1, H0, third entry H2, H1, H0 and so forth, correct. And you can please go ahead and write down all the equations. Now if I had padded myself, if I had to do 0 padding, I would have had to pad with 4 zeros, 1, 2, 3, 4. If 4 zeros were present, that means my matrix does not start from here, it actually starts from a little bit ahead. So the matrix actually will be H0 here, H1, H0, H2, H1, H0 and one more row, and by the time it came to this point it would have H4, H3, H2, H1, H0. Okay. So that is what the 0 padding will do, and this is you can verify that this is indeed the case. Okay. Any confusion? Oh, sorry, it's C. Sorry, I tend to use H for channel, so in this particular example we have been using C. C1, C0, I apologize. Okay. We should C2, okay. Oh, I have got lots more to change. Okay. Sorry about that. These are all the C's, C4, C3, C2, C1. Now we have to eliminate these. Okay, I hope this is okay now. This is C0, C1, C0, C2, C1, C0 dot dot dot. Okay. And the last of the entries that we would be working with would be C0, C1, C2, C3, C4. Okay. And you will basically get the toplet structure, and you can see the toplet structure that is emerging. Okay. So, the reason for this is not that, I am sure you know how to do linear convolution, so that is not the purpose for this. As always, there is a specific reason. Now, if I had to do cyclic prefix, what would be these 0 samples would be replaced by, the first one would be replaced by x7, the one previous one by x6, x5, x4. Okay. Now, and I throw away the first how many elements when after I do this with the cyclic prefix, I will throw away the first new entries. So, which means that when I look at the output of this matrix product, the first new rows are not important to me. So, where does the new cutoff come in? The first new rows are here. These are the first new rows. Okay. Beyond that will be the rows of it. So, basically these rows are something that are not of interest to me, because I am going to remove that. So, what I am left with is this matrix, the remaining rows, okay, multiplied by the circular convolution, multiplied by this with the cyclic prefix. Okay. You will see that now what is C1 multiplying here? When I multiply with this, C0 is multiplying x0, C1 will multiply x7, C2 will multiply x6, and so on. Okay. Now, this matrix operation can also be, you can please verify, this is very important, you can also implement it in the following way. H0, again I am writing HC, C0, C1, C0 dot 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 all the way to C0 here, C1, C2, C3, C4, and right at this point where I get no, I should get above C3. So, right above C3 I will get C4 here, C3, C2, C1. Okay. I am going to fill this up in a minute. This is the input vector x0, x1 through x7. Okay. This is C0, C1, C2, C3, C4. Basically, you will have this as a toplets matrix. This is C3s. The first column, this column corresponds to, so basically what you will have, if I wrote down this row, you would have C0 here, C1 here, C2 here, C3, and then C4 actually has gone up to the top. Now, if you check these equations, you will get exactly the same output as this. Now, basically what we are showing is this is a compact form representation of what was the computation that is done in the previous case, only applicable when I have done a cyclic prefix, right. I have inserted the cyclic prefix and I have thrown away the first new rows. The remaining computation can be shown to be equivalent to this. Okay. Now, if this is the case, then I want to go in and look at this matrix. This looks like the pseudo circulant matrix, except there is no Z inverse sitting on top. This is actually a straightforward circulant matrix. So, this is a circulant matrix. So, the important thing that we observe is that the whatever linear convolution that we were trying to do can be represented in this form where you have a circulant matrix times the data. Now, if you go back and recall the process or properties of the DFT, when I do pass a signal through an LTI system, I get linear convolution. But if I multiply the DFT of 2, the input sequence and the impulse response, what do I get? Circular convolution. And how did you represent circular convolution? It would be in the form of a circulant matrix times this, or a periodic extension of x of 7. And cyclic prefix is nothing but a periodic extension of x only to the extent that you need to obtain circular convolution. So, this is actually with the cyclic prefix, the linear convolution that happens in the channel now has become a circular convolution. Okay, very, very important observation, circular convolution. Okay. So, what is the length of the data sequence? Length of data sequence in this case was 8. Okay. Length of the impulse response or the channel impulse response of the channel, length of the channel was actually equal to 5. But when I want to do circular convolution, then I add 3 zeros plus 3 zeros padded. Okay, so then I will get this also to be of length 8, length 8. So, notice that if I filled in this, there will be 0 0 0 in my matrix. Those are the entries that we have kind of omitted. So, basically and when I do circular convolution of a data sequence of length 8 and an impulse response, circular convolution will give me another sequence of length 8. So, the length of the circular convolution output does not increase in length, it always remains the same. That is one of the properties of circular convolution. So, this is circular convolution is also equal to 8. Okay. So, here is a very important statement that we are going to make. Please make sure that you are comfortable with this. First step was to add cyclic prefix. How much cyclic prefix to be added? This has to be greater than or equal to nu, which is the number of ISI taps, number of ISI taps. Okay, the cyclic prefix has to be greater than or equal to. Under that condition, the length of cyclic prefix greater than or equal to the ISI, the channel does circular convolution, sorry, linear convolution. In the channel does linear convolution. So, in the channel we have linear convolution, but after CP, the portion with CP, if the first new terms are removed, actually what we are left with is after removing the first new or the CP portion, okay, because CP we said after removing the length of CP, after removing length of CP terms, then what we are left with is circular convolution of the channel with the vector, circular convolution. Circular convolution. Okay. Now, probably still at this point not really very clear where we are heading with what we are discussing and how to build upon this. Okay. Now, can you as an exercise, I would like you to draw a structure that introduces redundancy, which is of the form of the cyclic prefix. So, basically you will go back to this type of a structure where the last new elements will get added to the front. So, basically remove this red portion, add the cyclic prefix which will be at the top, and then so maybe if I just indicate it to you, I would request you to finish the rest of this part. Okay. So, the part that we want you to introduce is the following. So, you have the original input data, that is S naught of n, which will be passed through the, wait a minute, correct, okay, S naught of n, S1 of n, S m minus 1 of n. Now, the cyclic prefix will get added at the top. So, the redundancy I am kind of showing it in the other direction, because these are the m samples, and here are the new CP. This is the m data samples. In this case, it will be S naught, S1, all of those plus the cyclic prefix. Once you have the cyclic prefix, each of these, this is where the redundancy is coming in, upsampled by n, next branch upsampled by n combined with a delay element, okay, and please implement it all the way down to the last branch, upsampled by n with a delay element. It is helpful for us to sort of make sure that there are no confusion or doubts as to where the redundancy is coming in. Okay. So, and this is what will go through the channel C of z. This is what will become, it should be a linear convolution of this sequence, but at the output, once I take out the first new samples, it becomes circular convolution. So, again I am not indicating the noise at this point. Then on the other side, we will do a downsampling by n, an advance operator z downsample by n dot dot dot, and you get these outputs, advance operator downsampled by n. Okay. The first new entries I throw away, new samples throw away. What is left with are the remaining m samples, and this is what we are going to use for the processing. This actually represents now circular convolution with the data, with the channels, channel impulse response, circular convolution. Okay, I would like to leave you with a very interesting and a very important result, and hopefully this is a good place for us to pick up in the next class, but it's a extremely interesting observation. Okay, so I still have a few more minutes. So, the generation of cyclic prefix, okay, matrix form. So, the generation of cyclic prefix, I would like to show it in matrix form. Easy enough, but it is good for us to visualize this. I will show it as a matrix that operates on the input vector. F times, I will call it Cp to show that this is the one that generates the cyclic prefix. It is a matrix that must have a dimension n cross m, because it will take in m samples and produce m samples with the cyclic prefix. It is going to have the following structure. The upper right hand is a diagonal matrix of new identity elements, identity matrix of dimension I nu. Then I have a I m minus nu here, followed by a I nu. Okay. So, m plus nu is n. So, therefore, you can verify that and this inner matrix of course is nothing but an identity matrix of dimension m. Now, if this operates on a vector which is it S vector that it operates on? Yes, it operates on S. Okay. It operates on S naught of n S m minus 1 of n. If this operates on, you can please verify that this actually produces for us, this vector does not get touched, this portion of the vector remains, that is what the lower identity matrix preserves. This is S m minus 1 of n. The one just above that where the cyclic prefix is getting introduced will be S m minus 1 of n all the way up to S m minus nu of n. So, you can verify that this is exactly the cyclic prefix portion. Okay. Now, what is the part that we are going to be looking at? Basically, what we have is that the input vector x is equal to this matrix FCP operating on S, that is the input matrix. Now, this passes through the channel. Okay. So, this x of n passes through the channel CP C of z, passes through the channel C of z, passes through the channel C of z, and then I have to do CP removal. Whatever is the first new samples I have to remove. So, this is how I am going to do CP removal. Let me call the vector that is where the CP has been removed as r hat, that will have dimension m cross 1. I am going to construct it by killing the first few elements. So, basically there is a 0 matrix of dimension nu cross nu, followed by an identity matrix of dimension m multiplied with r of n, and this is a n cross 1 vector. Okay. And you can easily visualize that basically the first new rows new entries of r of n will not show up at the output because they are getting multiplied by zeros, and what is left, and this is of course a matrix of dimension m cross n. Okay. So, very important that now we go back and look at what actually went through the channel. What went through the channel was x of n. So, like before, if we wrote down the equation, r of z will be equal to CPC of z times S of z. Okay. I hope there is no confusion as to what the notation is, and no, it is x. We have inserted the cyclic prefix. So, therefore, this should be x of z. Okay. Now, very important, go back and look, because when the output comes from this computation, whatever this computation is, when the output comes of this computation, I am going to do CP removal. CP removal means the first new elements are going to be thrown out. So, which requires us to go back and look at CPC. Okay, again leave it at this point, but so if you go back and look at the CPC, we did this matrix yesterday. Previously the 0 padding eliminated the last new columns, but now the CP removal part, which portion is going to, which is it going to remove? It is going to remove the first new rows are going to be eliminated. Okay. So, what you are going to be left with is, if you notice, the Z inverse terms all occur in the upper new rows of the matrix. So, if I have removed that, Once again interblock interference is gone, even through the cyclic prefix method, the interblock interference is gone. What we are left with is a matrix that what remains is the one that we can now say that it's a constant matrix which we now have to which we now can work with. So the constant matrix is the one below the red line, whatever is it's a banded diagonal banded Toeplitz matrix which we can then now leverage. So I will leave it at this point just to get a feel for make sure you get the whole picture together. What does that F matrix does, how does it insert the cyclic prefix, then how do you remove the cyclic prefix, and then when you look at the cyclic prefix terms, the CPC of Z, the first new rows are getting eliminated. So then what is left with is a constant matrix times that. So which you can now say that after CP cyclic prefix removal, it becomes once again a simple linear equation, a set of equations where there is no interblock interference. Okay, so we will leave it at this point, but we will pick it up from here because we are one step away from the answer that we need, and we will complete this in the next class. Thank you very much.